Hi, and welcome to this section of the Advanced Calculus 2 tutor. And in this section, we're going to continue developing our skills with trying to understand when series converge and when they do not. And we're going to talk about the comparison test, the so-called comparison tests of series convergence. So in the last section, the main thing that we introduced was the integral test, which is basically you can take the integral of the equivalent function that would look like the terms in a series, and if that integral converges, then the series also converges, okay? And we know how to take integrals, so that's sort of a pretty bulletproof way to figure out if a series converges or not. Unfortunately, sometimes the integrals are going to be hard to find by hand. You know, there's lots of integrals that you can't ever find by hand. You have to use a computer to find them, and so it's not very helpful if you can't calculate the xy graph here. And this is n, and this is you know, the term in the series that we care about, okay? Let's say I'm trying to study, a sub n, which is a series, right? And let's say that the, you know, n is equal to 1, 2, 3, 4, 5, 6, 7, whatever. You know that the terms of a sub n do something like this. They approach 0. But that's not enough to tell you if the thing converges or not, just if the terms approach 0. You must have the terms approach 0 in order for the thing to have a hope and a prayer of converging, but it doesn't tell you by itself. Be less than b sub n. A sub n must be less than b sub n for all n, every single value of n. So it must kind of parallel as it comes down here then. So what this thing is saying is, let's just read it. Suppose the two series a sub n and b sub n, which are given here on the graph, have positive terms, which they do, if b sub n, which is the blue dots, is convergent. If that series converges and a sub n is less than b sub n, like I've drawn it here, for all n, then you have proven that a sub n converges. Another way to look at it is, look, I've got two related series. The red series is the one that I care about. That's the one given to me on the test. Dots here at the various values of n. And the series that I have invented to compare it to would be on top, just like before, because the terms are just laid out that way, okay? Now let's look at b sub n and see what kind of series it is. It looks very familiar, but it is not a p-series, because a p-series is 1 over n raised to a power, and this is 1 over a number raised to n. If you go back and look at the geometric series, it is a geometric, or it looks like, I should say it looks like a geometric series, okay? The geometric series, remember, limit is equal to a number greater than 0, then it means either both of these things converge or they both diverge, okay? So if you can find b sub n converges, then you approve a converges in this case, and vice versa. But both of these things have to be, both of these things are true if the limit converges to a number, and that number has to be greater than 0, okay? So that was part A. Now over to part B, okay? If the limit as n approaches infinity of a sub n over b sub n, the elements, is equal to 0, exactly equal to 0, okay, and bn converges, okay, then a sub n also converges. Okay, so it's another if statement. If the ratio of the terms, and these are the terms, by the way, these are not the summation, this is just the ratio of the terms as n goes to infinity approaches 0, and you can prove that b sub n converges, then a sub n also converges. Okay, now part C, and this is the final part. If the limit, I bet you can guess, n approaches infinity of a sub n over b sub n is infinity, so it diverges. Okay, so if the ratio of the elements here goes to infinity, and you can prove that the sum b sub n diverges. Okay, so they're a little bit symmetric. There are 3 cases. You really should write them down and try to memorize them, and we're going to work some problems here to get some practice. So let us say we have the sum from n is equal to 2 to infinity of the square root of n over n minus 1. Okay, now the fact that this goes from n is equal to 2 to infinity doesn't really matter, you see. I mean, they'll probably give that to you on your test just to see if you get choked up over that little thing. I mean, yes, it does make the series different, but we don't care about what the thing adds up to. We care if it converges or not. So the fact that there's an extra term missing doesn't matter. That extra term is not going to make the thing diverge or not. It's the behavior as you go to infinity. So really just keep that in mind, okay? So what we're going to do is we're going to try to choose a b sub n. That's the first thing. This is a sub n, and we're going to try to choose b sub n because we want to find something to compare it to. My recommendation to you when you're using the limit comparison test is to choose b sub n by retaining to the 5th power plus 4. Okay? Well, the first thing I'm going to do is I'm going to try to find a b sub n. Okay? Try to find a b sub n, but before I even do that, I never like radicals running around my series. So it's 1 to infinity of n over n to the 5th plus 4 to the 1/2. Okay? That's what I have. And I'm going to try to find b sub n. And remember, what you want to do for b sub n is you want to try to retain the largest powers of the exponents in the top, or the terms that contain, to choose the highest powers in the top and the bottom, and in this case you just want to keep the square root around because that's effectively going to chop down that 5th power there. So it's n over n to the 5/2. Okay. So the next thing you want to do is you want to go off and see if this thing converges or not. Okay. You can see that this is going to reduce to 1 over n to the 3/2. Okay, you can see that it reduces to that because basically what you're doing is you strike this out and you're subtracting 1 from the bottom. So 5/2 minus 1, you would have 5/2 minus 1 to the 5th power plus 4 to the 1/2 all over what I found for b sub n, 1 over n to the 3/2. Okay, and what I want to do is figure out what that limit equals. So let's go ahead and do that. Let's flip this guy over and bring it onto the top. So it's going to be limit as n goes to infinity of, when I flip it over and multiply it, I'm going to have n times n to the 3/2 over, flipping it over, the denominator here, which is n to the 5th, the ratio of the elements, and we got a limit greater than 0. So now we're in the case where either both series converge or both series diverge. Okay? That's the case that I can combine them all under one common radical, and then I can do some more simplification and get it into the form where I can take the limit very, very efficiently. So in this section we have covered something very important, which is the comparison tests. And what we're doing is we're basically picking another series that's generally related to the series we care about. And in the first type of comparison test, we're looking, if we're trying to find a series that either lies all above the series we care about or all below, and we're looking at that behavior of b sub n, and if it squishes it down, then it forces it to converge, and if it things about b sub n, which will tell you about a sub n. So there's no silver bullet to this stuff. I mean, that's why Advanced Calculus 2 is pretty tough, because in these sections you're learning all of these different ways to test for series convergence, and sometimes it's hard to know what to use. I mean, it really is, especially when you're on a test, when you have all of them in your tool bag and you really don't know what he wants you to use, what the teacher might want you to use. And so either you see it or you don't. The only way you can get there is by working a ton of example problems, get some experience, okay, and then when you're on your test, when trying to find series convergence in Advanced Calculus.